Today we are going to start the concept of antiferromagnetism in the chapter magnetism. Actually, in this first lecture on antiferromagnetism, we will discuss only a short introduction regarding this antiferromagnetism. In fact, you know, the general condition for ferromagnetism in Heisenberg model is that the exchange integral Je should be positive, okay? And when the exchange integral is positive, then the internal field is parallel to the alignment of spins, and whole system prefers to take up the configuration of of the above figure, as you can see here. In fact, when you talk about ferromagnetism, then you know the appearance of very large magnetization is due to the parallel alignment of neighboring magnetic moments by exchange interaction, or in other words, the internal field in ferromagnetic material arises due to the exchange interaction that line up neighboring spin moments. And for such cases, as stated earlier, the exchange integral is positive. So you can see I have shown the spin arrangement in a crystal which is of ferromagnetic nature, and you can see here that all the spins are parallel to one another, as you can see in this figure. So in this condition, since the spins are parallel, so if we talk about the total spin, that is sum of spin Si over I, where I represents actually the ith spin, that will be simply equal to S1 plus S2 plus so on plus Sn, if you consider that the number of spins is equal to n. Okay. So if all the spins are of equal magnitude, then this will be simply equal to ns. Okay. That will be equal to ns if S1, S2, S3 all are equal to S. Okay. So in this condition, even in the condition of zero magnetic field, if the material is not subjected to the external magnetic field, even then, due to this particular alignment of a spin, the net magnetization is not zero. So there will be a net magnetization M which is not equal to zero even when the external magnetic field is zero. And this is the cause of the high magnetization of ferromagnetic material. Okay. These things we have already learned in our previous lecture. But in some compounds of transition metals, the spacing of the magnetic ions is such that the exchange interaction is negative, not positive. In case of some compounds of transition metals, it is found that this exchange integral Je is negative, not positive. And below a particular temperature, which is actually called Neel temperature, and it is denoted by the symbol Tn, it is seen that the spin arrangement is like as has been shown in this figure. You can see that the adjacent spins are in opposite directions. Here, this first spin you can see, if you consider is upward, the second spin is downward. Again, this third spin is upward, the fourth spin is downward. In this way, all the spins are arranged in a crystal. And the magnitude of the spin vector is also same. So in this condition, what will happen? If you will now find the total spin, that is sum of Si, okay, where I runs from 1 to n. In that condition, this sum, which is S1 plus S2 plus so on plus Sn, this will be equal to 0, because you can see the vector sum of the spins of two adjacent spins will be 0 because the vectors are of equal magnitude and opposite direction. So they will cancel one another. So it is obvious that when no magnetic field is applied to such a material, H is equal to 0, the net magnetization will be equal to 0. Okay. In fact, such a material where the spins are arranged in this particular manner, that materials are called antiferromagnetic materials, and such a phenomenon is known as antiferromagnetism. Okay. So I have mentioned it here. You can see that in some compounds of transition metals, the spacing of magnetic ions is such that the exchange integral Je is negative, and below a critical temperature Tn leads in a certain structure to anti-parallel alignment of electron spins in the neighboring atoms, as so you can see in this figure. Okay. So this phenomenon is called antiferromagnetism, and such a system is called antiferromagnet. Okay. Thus, you can say that antiferromagnetism arises due to the opposite alignment of adjacent atomic magnetic moments in a solid produced by exchange interaction. Okay. In fact, when this material will be subjected to the external magnetic field, then what will happen? Actually, due to the external magnetic field, the spins which are actually in downward direction, they will also tend to align parallel to the magnetic field. So if a magnetic field will be applied in upward direction, okay, that is in the direction of a spin, then there will be the alignment of downward spin 2 in upward direction, and so then a net magnetization will be developed. Okay. So these type of materials, that is antiferromagnets, does not show any magnetization in absence of magnetic field, but in presence of magnetic field they will also have magnetization, okay, and magnetic susceptibility. Now actually we will talk about a third type of magnetic material also, which will be actually dealt after the concept of antiferromagnetism, and that is called ferrimagnetic materials, and the phenomenon exhibited by it is called ferrimagnetism. Actually, this ferrimagnetism is a special case of antiferromagnetism. Okay. So actually what happens in case of ferrimagnetism? You can see the ferrimagnetic ordering has been shown here, and this is almost like the antiferromagnetic ordering. You can see the adjacent spins are in opposite direction. You can see that this first spin is if upward, the second spin is in downward direction. Again, this third spin is upward, then fourth is in downward direction. But there is a difference between this ferrimagnetic ordering. Here, the magnitude of the spin which is upward and which is downward are not equal. Okay. Since the magnitude are not equal, so when they will added vectorially, the result will be not 0. Okay. So as in case of the antiferromagnetic materials, all the vector sum of all the spins becomes 0. But in this case, can you say that the vector sum of all spins will be 0? Answer will be no, because the number of up and down spins are equal, but their magnitudes are not equal, and therefore there will be a net magnetization even in absence of the external magnetic field. So in this case of ferrimagnetic material, when H is equal to 0, it means no magnetic field is applied, even then net magnetization M is not equal to 0. Okay. So I have mentioned it here. You can see A special case of antiferromagnetism is ferrimagnetism, where opposed moments are of different magnitudes and a large net magnetization thereby results. Okay. In other words, you can say in antiferromagnetics, spins are balanced. Okay, up and down spins are balanced, whereas in ferrimagnetic materials, spins are unbalanced, not balanced, due to the unequal magnitude of the up and down spins. Okay, and that's why a considerable amount of magnetic moment is present in this ferrimagnetic material. Okay. Now we will see how the magnetic susceptibility depends on temperature in case of the ferromagnetic material, antiferromagnetic material, and ferrimagnetic material. Actually, you have already discussed this variation of magnetic susceptibility with temperature in case of ferromagnetic material, but here for a comparison I have shown the graphical plot of the magnetic susceptibility chi in against of temperature in case of the ferromagnetic material, antiferromagnetic material, and the ferrimagnetic material. Okay, and I have also shown here the magnetic ordering also. You can see when you talk about the ferromagnetic material, then when chi, that is magnetic susceptibility, is plotted in against of temperature T, then below a particular temperature which is called critical temperature Tc, okay, we cannot say how this chi varies with T in an exact mathematical form. The exact mathematical relation between chi and T below this temperature Tc is unknown till now. We don't know. Okay. We simply say that below this Tc the variation of chi with T is in a complex manner. Okay. So in this figure you can see the curve has been not shown when temperature is below this Tc. Okay. But when temperature is raised from Tc, that is T is greater than Tc, then you have already studied earlier that the magnetic susceptibility is related to the temperature with a particular relation which is called Curie-Weiss law, and this Curie-Weiss law is mathematically given as chi equal to C over T minus Tc. Okay, chi equal to C over T minus Tc, where C is actually Curie constant. Okay, and so with increase in temperature you can see this Tc has a particular value for a particular ferromagnetic material, although for different ferromagnetic material it is different, but for a particular material it has a particular value. So it is obvious from this Curie-Weiss law, with increase in temperature this chi will decrease, okay, and non-linearly. Okay, so this graph is almost in fact in hyperbolic form. You can see this is the case of variation of magnetic susceptibility of ferromagnetic material in against of temperature T. Okay. Now in the similar manner, when you talk about the ferrimagnetic material, almost same situation is found here. Almost same, not exactly same. Again it is seen that below this temperature Tc, which is again called critical temperature for ferrimagnetic material, the variation of chi in against of T is not exactly known till now. We can simply say that at temperature Tc or at a temperature below Tc, the magnetic susceptibility of ferrimagnetic material or ferromagnetic material is very large. Okay, but when temperature is increased from this Tc, then again you can see that this susceptibility decreases. Okay, but what is the exact relationship between temperature and chi? You can't predict. Okay, but it is found from experiment that it decreases. Okay, so this is these are the cases of variation of magnetic susceptibility with temperature T in case of ferromagnetic material and in ferrimagnetic material. I have shown here the spin ordering here, and you can see there are actually up and down spins, but the magnitude or the length of the spins are not equal. Okay. Although our prime aim in this lecture is to introduce you the concept of antiferromagnetic material or antiferromagnetism. So now let us see this figure which I have shown in B. This is the graphical plot of magnetic susceptibility of an antiferromagnetic material in against of T. And you can see from this graph that this variation of chi with T is entirely different from the variation of chi in case of ferromagnetic material and ferrimagnetic material. You can see that the most remarkable fact of this graphical plot is what? You can see that the important point to note is that the susceptibility curve of antiferromagnetic material has a peak at a certain temperature. You can see this is the peak point P, and corresponding to this point P, the temperature is Tc, which is actually called Tn, and that is called actually Neel temperature. In fact, in our second lecture, when we will actually discuss the proper theory of this antiferromagnetism, which is called molecular field theory, then we will discuss in very detail this Neel temperature. So it is seen in case of this chi that at this particular temperature, which is called Neel temperature, denoted by the symbol Tn, which has also a particular value for particular antiferromagnet, it is found that this chi is maximum. Okay, and at temperature below this Tn and above this Tn, the value of chi decreases. Okay, so when you will look at this second figure, you can easily see that when there is no external magnetic field, then magnetization of antiferromagnetic specimen is definitely zero, because the moments exactly cancel when summed up over the entire crystal. You have seen. Okay, but if the field is applied, then a small magnetization, which is in the direction of the field, will be resulted. So I have shown that magnetization is not zero, but it has some value here. So chi is non-zero, I have shown. Although it is possible that if you start from zero magnetic field, then this curve may start from this origin. It is possible. And with increase in temperature, this magnetization increases. When magnetization will increase, this susceptibility will also increase. And in this way, this magnetization increases as the temperature is increased. And finally, a temperature is reached at which the magnetization is maximum. And that very temperature is called Neel temperature. And above this temperature, you can see that this magnetization or the magnetic susceptibility decreases, as you can see, when temperature is actually made greater than this Tn. Okay, and with further increase in temperature, okay, and this particular temperature where this magnetic susceptibility of antiferromagnetic material becomes maximum, as I have told you, this is called actually the Neel temperature. Okay, and it is denoted by the symbol Tn. and this Tn has a particular value for particular material. You will see that a very good example of antiferromagnetic material is MnF2, and for this the value of Tn is 72 Kelvin. Okay, and in this way for different material the value of Tn will be different. Okay, now the corresponding susceptibility variation which I have shown here, the peak occurring in this curve is at Tn, and is the most characteristic feature of antiferromagnetism. Actually there are other characteristic feature of antiferromagnetism too, and they are actually the anomalies in the heat capacity and thermal coefficient of expansion, which we will discuss later on. Okay, so from these three figures you can differentiate the three type of materials: ferromagnetic material, antiferromagnetic material, and ferrimagnetic material. I have shown the differences by this graphical plot of chi in against of t. Okay. Now, actually for your convenience, I have mentioned all these facts here, and you can note down these things. Okay. Now let us see a particular example by the experimental data here. Actually, in this figure, I have shown the variation of the molar susceptibility, which is denoted by the symbol chi-m. When you say molar susceptibility, that means this is the susceptibility for 1 mole of the substance. Okay, and this graphical plot has been shown is actually for the antiferromagnetic material named MnF2. Okay, you can see from this figure that below this temperature Tn, which is called Neel temperature, and which is actually 72 Kelvin for this MnF2, there is no simple law for chi-m which can be predicted how this chi-m varies with temperature. There is no particular mathematical law. Okay, but when you talk about the temperature which is greater than this Tn, then actually this magnetic susceptibility chi-m varies with temperature in accordance with a particular mathematical law, which is given by chi-m equal to C over T plus theta. Okay, here actually theta is positive. Okay, not negative, but theta is positive. Okay, and so with increase in temperature, you can see that this chi-m will decrease. Okay, as I have shown in this figure. Okay, one thing here is also to be noted here, that below this temperature Tn, you can see I have shown two curves, not only one, but I have shown actually two curves, and both of these curves are actually get coincided at this temperature Tn when this chi-m is maximum. Actually, these two curves are due to the different magnetic field. It is found that when temperature is less than this Neel temperature Tn, then the magnetic susceptibility and its variation also depends on the value of the external magnetic field. Actually, in this figure, this upper curve, or you can say that the upper branch, corresponds to a magnetic field whose strength is 2 into 10 to the power 4 Gauss. Okay, this is an experimental data, and this lower branch is for the magnetic field H equal to 400 Gauss. Okay, so it is a very important fact that at low temperature, that is at temperature below the Neel temperature, chi m depends slightly on the field strength. Okay, and so for different field strength you will have different curves. Okay, so these are the some of the important facts regarding this antiferromagnetism. Okay, and as I have told you that in our forthcoming lecture we will start the proper theory of this antiferromagnetism, which is actually called molecular field theory. Okay, and we will discuss the magnetic susceptibility of antiferromagnetism, particularly in two cases. The case will be when T is greater than Tn and when T will be less than Tn. And we will also discuss in very detail what is this Neel temperature, how we can measure this Neel temperature, what are the factors that affect the Neel temperature. Everything will be discussed in our forthcoming lecture on antiferromagnetism. So this was just an introduction, a very short introduction regarding this antiferromagnetism, and I hope you have definitely enjoyed it. Okay, thank you very much.